Okay, today we are finishing up 9.3. We're going to continue on with our probability, and we're focusing on compound probabilities. So last time we were focusing on just one thing happening. What's the probability of a dice rolling a 4? What's the probability of drawing a red king? But now we're doing two or more events. So we're doing compound inequality today. And so first thing, compound probability. First thing is we need to define what a compound event is. A compound event is two or more simple events, and they can occur at the same time. We're going to talk about a lot of examples with these, so if you don't already know what's going on, just hang tight. So the first type of these kind of probabilities we're going to look at is we're going to see the probability of either two events happening. So either this occurs or that occurs, and then both of those count as successes. Both of those are okay for us. So the probability of either of two events happening, which means it's a success. In order to find this probability, we are going to add the two probabilities. So that's going to be important in a second when I tell you another type of probability. So this one is where we add them. You hopefully saw the Venn diagram video, and if you haven't yet, watch that shortly. But I talked about doing A or B. So this little value that looks like a U, that means or. So if it's okay that we get A or B to be true or to happen, then we can find that by doing the probability of A plus the probability of B. What we are going to have to do when we do this algebraically, if they are not mutually exclusive, if there's an overlap, we're going to have to minus off the overlap of A, probability of A and B happening. So that's my overlap values. And we'll do an example in a second so you can see what I'm talking about. And this is where they are not mutually exclusive. Not mutually exclusive. I like to think about it just as if there's an overlap. If you look at both sets and there's something or some things that are in both sets, then we have to subtract it off. If we happen to have mutually exclusive events that don't affect each other, still I'm going to think about it as P, a probability of A or B. But in this case, if they are mutually exclusive, then we get to just add the probabilities together. Probability of A plus probability of B. Since there's no overlap, we won't need to take anything off. So I'm going to label this as mutually exclusive. I'm going to label it as yes, mutually exclusive. Okay, I don't know if your screen is frozen, but it looks like it's frozen here. Come on, let's go. I hope it's going to catch up, but I don't know. How are we doing? Oh, there we go. Okay. Yes, mutually exclusive. Okay. So now let's do an example of these. So I'm going to give you, well, our whole example will be rolling a dice. Okay. I'm just going to go over here. So follow me over here. So I'm going to do an example. So we're rolling a dice, a normal 6-sided dice. All right, my sample space, which means all of my possible options, includes what? Normally we don't list it because we're really familiar and very comfortable with the die, but if I were to list it, my sample space is 1 through 6. So every number 1 through 6, there's a side of the die that has those numbers, okay? Let's pretend that in order for us to have a success for maybe set A, we're just making stuff up. I'll say that I need to have 2, 3, and 6, okay? In order to have set B, we're gonna say now to be successful, it's gonna be 2, 4, and 6. So those are two different things. So I could find the probability of A, which I'm going to do over here. So we'll say probability of A. What's the probability that I'm gonna roll a 2, 3, or 6? Yep, 3 over 6. There are 3 different options out of my 6 sides. 3 out of 6 is my probability of rolling A. Probability of getting B is the same, right? 2, 4, 6. Those are 3 sides of my 6 sides. So it's also 3 over 6. Okay, if I'm going to do the probability of them together, probability of A or B, that means that I'm going to add them together, probability of A plus probability of B. Am I going to have an overlap here? Is there something that I'm going to have to take into consideration? Are there numbers that are in both of the sets? Yeah, right? 2 and 6 are in both of the sets. So I do have an overlap. So I'm going to have to minus off probability of, oop, I ran out of room. Let's move everything over. Scooch. Okay. Probability of A and B, I'm gonna have to minus that off. So we know probability of A is 3 over 6. Probability of B is also 3 over 6. And then probability of them together is going to be how many out of 6? How many are overlapping? 2, right? 2 over 6. So add, minus. 3 over 6 minus 2 over 6. 3 plus 3 is 6. Minus 2 is going to be 4 over 6, which simplifies down to be 2/3. So that's my answer right there. That's my probability of those events. So this one was not mutually exclusive because we had an overlap. So maybe you want to make a note on your paper next to this. This was an example of not mutually exclusive because there was an overlap. That might help. Okay. Let's go again. A few more examples up our sleeves here. Okay, example. We're rolling a die again. And I want to know what's the probability of rolling an even number or a divisor of 10. Whoa, come back. Rolling an even or a divisor of 10. Okay, so we can think of set A as being rolling an even. So what are my options for set A? What would be a success if I rolled an even? Yep, 2, 4, and 6. Those are all even numbers. Okay, what's a success if I roll a divisor of 10? Well, if you don't remember, that's probably like a middle school word, divisor. That's a number that we can divide by 10 and get a whole number. So if 1 through 6, what divides by 10 and gives me a whole number? 1, 2, 5. Awesome. Okay, so now we're going to find the probability of A or B. I know I'm going to have to do probability of A plus probability of B. My question is, do I have an overlap? Are these mutually exclusive? The answer is yes, there is an overlap. 2 and 2 overlaps. So I am going to have to minus off A and B where they overlap. Okay. Probability of rolling an even, 3 over 6. Probability of rolling a divisor, also 3 over 6. This time my overlap is just one number, so I just have 1 over 6. That's my overlap. So add minus 6 minus 1 is 5 over 6. And then this one is also not mutually exclusive. I don't feel like writing all that down, so I'm just going to draw another arrow. Okay. All right, and then one more example of these before we do a couple more things. Here we go, an example of, let's say this time we're rolling 2 dice. Roll 2 dice. And we want to find the probability of rolling a sum of 7 or 9. What's the probability if I roll 2 dice that I'm going to get a 7 or 9? Okay. This time we're going to call A rolling a 7. If I rolled a 7 and I rolled 2 dice, my first dice could be a 1 and my second dice could be a 6. I could roll a 2 and a 5. I could roll a 3 and a 4. Okay, now these are technically all my options, but we can also switch all of them because these 2 dice look different. So like I have my first number is like my first dice and my second number is my second dice. Well, while I have all these listed, I could also have rolled a 4 on my first dice and then gotten a 3 on my second dice. So we kind of have to do all of the reverse of them too. 5, 2, and then 6, 1. And that's a total of how many times? 1, 2, 3, 4, 5, 6. So 6 different ways that we can get a 7. What about if our B section then was 9? What are all the ways we could get 9? Okay, well, 1 plus 8 would be 9, but there's no side that's an 8. Okay, well, let's think about something else. 3 and 6. And 4 and 5. I think that's it. Okay, reverse them. 1, 2, 3, 4 options. 4 ways that we can get those. Okay. If I'm going to do the probability that A and B are happening, excuse me, A or B, or I don't know why I messed that up. A or B is fine. So you're either rolling a 7 or a 9. Those are both cool options. So we're going to do probability of A, which is what over what. I'll just write it out like this first. Probability of A, and then plus probability of B. Whoa, what's happening? Okay, there we go. Do I have an overlap here? Do I have any matches here that are the same? No, right? None of them match. I've got 3 and 4. I've got 5 and 4. Those aren't the same. 3 and 6, 1 and 6. Nope, those aren't the same. I don't have any overlap. So I'm not going to minus off anything. So since there's no overlap, I'm done here. I'm just going to add my 2 probabilities together and call it a day. 6 over, well, how many options are there? You can think, well, there's 6 sides of one die, 6 of another, multiply them together. Or you can go back to your other notes. Where did we do those? Oh, right here. This is where I made my sum table. So my notes are helpful. Refer back. You can count all of these up again, and there are 36 different options. You'll also see that while we counted them out, you could have used this table. For 7, I've got 1, 2, 3, 4, 5, 6 options, and for 9, I have 4. That's what we counted out without a table, so you can use a table if that helps you keep yourself organized. So 6 out of 36 options give me a 9, or give me a 7, excuse me, and then 4 out of 36 give me a 9. So when I add those two together, it becomes 10 over 36. And if I simplify that, it becomes 5 over 18. That's the best answer. Okay. Now we're going to talk about multiple probabilities. So these were just compound probabilities. Now we're doing multiple probabilities. This is when 2 events are independent, mutually exclusive, and I've got like another little form. So maybe I'm going to go back and highlight these 2 because we're going to use those again later, and I'm going to teach you other ones as we go. So these were of 2 events that were or, so we added those. Now we're doing multiple. Wow, let's be a little neater. Multiple probabilities. So this is when we have 2 events that are mutually exclusive. And another word we're going to use here is independent. They're independent of each other. The event of one happening doesn't affect the other one. So a lot of times this is like with dice or with coin tosses, because if you toss a coin, it's not going to affect what the next coin toss is going to be. Okay, so we're going to do a couple examples here. So we'll say example. This example, we're tossing a nickel and a dime. And I want to know what's the probability that both will be heads. So when I toss a dime, I want to know what's the probability that it will be heads, and I'm going to toss a nickel, and I want it to also be heads. So let's think about it. Probability of a nickel being heads. Well, what's the probability of you flipping a heads? Any coin. Any normal coin. 1 out of 2. Same thing for the dime. In order to get a heads, it's also a 1 out of 2 probability. When we are doing this multiple probability with these mutually exclusive events and we're finding out the and, we are going to multiply them together. Oh, I got a little ahead of myself. I'll put this right in here. Probability of A and B happening is probability of A times probability of B. Let's move this guy over here. Let's move all of these guys down. Oop, I lost you. Okay, I'm not smart enough for that, whatever. Okay, so probability of A and B happening. In case we didn't watch the Venn diagram yet, this means and. So they're both happening and we are multiplying. Okay, so in order to show this, I've got both of these probabilities right here, 1 over 2, 1 over 2. So the probability that both are going to be heads, I guess we can say head, head, or something like that, is going to be 1 over 2 times 1 over 2, which is 1/4. This one is an easy one. We could have thought of this by hand. You could have done, okay, what are my options? I could do head, head. I could get head, tail. I could get tail, head. I could get tail, tail. And then you could see there were 4 options and I got 1. Now I could just ask for this on a much bigger scale, so it would maybe not be as easy to reason my way through it, but I am showing you that we have that as an opportunity as well. All right, I'm gonna go to the next page and do another example with this before we move on. Okay, example. In this case, I've got 2 dice. One has faces. So the first die has letters on its face. It has A, B, C, D, E, and F as its faces. The second die is a normal die, and it has 1 through 6 as its faces. So what's the probability? I'm going to roll both die. What's the probability that we roll D on my first die and an odd number on my second die? So if whatever I roll on the first die does not affect what I roll on the second die and vice versa. So I am just worrying about 1 die at a time. What's the probability that I'm going to roll a D? What's my probability that I'm going to roll a D? Well, there's only one side that has a D, so it's going to be 1 out of 6. Similarly, what's the probability that I'm going to roll an odd number? There are 3 odd numbers of my 6 sides. So I'm going to say 3 over 6. Is there any overlap here? No, right? The whole reason I changed it is so that I've got A through F and I've got 1 through 6. So what I roll on one die is not an option on my second die and vice versa. There's no overlap here. So I'm just going to be able to do um, well, actually, I'm going to do the formula I just gave you. I don't know why I said all that stuff. I'm just multiplying them together. I'm multiplying them together because I want both of those events to happen, not one or the other. I want both to happen. So I'm going to do probability of D and odd is going to be 1 over 6 times 3 over 6. When we multiply those two together, we get 3 over 36, and then that's going to simplify down to be 1 over 12, which is my final probability. All right, this is a lot for one video, so I'm going to pause this, and there'll be another video on part 2 of 9.3. So stay tuned.